So what I do is I'll put some thicker wire on one end to kind of hold it together, and but it gives me a little bit of movement. So as I wind the coil or the wire, it keeps it together and yet keeps it movable, flexible. So there's not a lot of space inside, but I did reserve some space inside to place things in it. And so here, I normally use from a taken apart record player. I place that with my, this is a 12-pound coil of cable, copper wire. It's 32 gauge. And here we see that the polycarbonate sphere that's printed, it's in the mold that I'm going to use to pour the two-part epoxy. And this turns really nice. It doesn't get any kinks in it or anything. And this allows me to sit and watch my iPad, some channels on YouTube, and chill and coil. One of the things I do is I put it on something that I can spin it, and then I put sandpaper. And so you can see how deep the grooves are. But sandpapering, it just makes it a lot smoother in the winding process. And so now I've applied some turns of the thicker wire, so it's being held together. Here's where my slides aren't in the exact order, but so the sphere is not transparent, but it's translucent. So I'm hoping to see some cool things inside, but a spoiler, this first attempt was a failure, but it was a fun failure. I originally tried winding it with the drill, and I kept having to unwind it and fix it. So it was taking more time to use the drill, so I decided to just use just to hand drill it. And so this is a way how not to wind your sphere with grooves because it just doesn't work. But cylinders, it would work, but not with the sphere. So this is about the time when I decided to take it away from the drill. This is how I'm hand winding it. This is pretty cool. I changed out the record player setup because I had turned the sphere into this setup. And so it's pretty cool because once you get it started, it'll actually go into the right groove, unlike the drill. There's give you some shots of it to show you how it's a pretty cool looking globe here. All right, so I'm going to kind of show you my setup and how I do things. You'll see that I have the variac there. That's the AC input. And here you can see that the oscilloscope is reading. I don't connect my oscilloscope. Oh, that's my, oh my goodness, ozone detector. I always turn that on before my experiments. This is my infrared camera. This tells me what components are overheating on the ZVS board. That way I don't have to lose the components. If I see something overheating, I'll just stop the experiment and see what's going on. And so I always have my infrared camera. Here you see that translucent globe putting out the same kind of plasma that I'm always outputting in my coils. And so this is just sort of what goes on in my lab. Again, this is the variac. I'm putting in pretty low voltage. It's actually too high. It's about 12 volts. And here you can see that this is a nice ring signal, not the best. Again, the ozone detector. Ozone, I like it because it'll tell you good, warning, and so on. And then the infrared here, I just want to show you the white part there. Those are the input diodes. Those are the things that fail first. So I keep an eye on them. This is the ZVS with the 4 MOSFETs. And then again, here's the sphere. So a little out of order here, but we're going to check this thing out. Here's a little bit of a close-up. Okay, so you can see first at the top, you'll see that there's a discharge. But if you look here in the middle at the hemisphere here at the equator, if you will, just below the equator, you'll see like a little white spark. This is a bad thing. So when I had encased this in epoxy, you can see that it didn't go over smoothly, that it sort of clumped on certain sides, and it's like full at the bottom, but it has this sort of thin spot down here. And then you can see here that there's plasma coming out where you don't want it. Um, this was a poor poor epoxy job. Um, and so it has a lot of problems, but I thought I'd share the issues with you because if you want to try this, then these are the things you want to look for when things are going wrong. You see that I'm also using the same bowl-shaped copper pipe, this concave here that I use for all my coils. It's pretty cool how the ZVS will just pick up and use whatever you put in front of it. And so I use this for most of my coils. But again, this is a bad thing. This little arc here, not desired because it'll eventually end up with more issues. So I took out my Tomlov microscope. It's about 3,000 magnification. And here you can see a close-up. Let's see if I can bring it in here. You can see a close-up here of the area that was sparking and arcing. Let me see, turn off my cell phone here real quick. You can see that there's some charring, which is the dark portions, and that it's like right here is where the wire looks like it's going to be severed. And so here I found the issue. And you can see how there's a nice glossy coat of epoxy over this, but it's not even. And so it lends itself to these kinds of problems. So I pulled out my trusty Spider-Man toothbrush, and with a little alcohol, I scrubbed the area of the char, and I marked it between these two red lines here. And here's the close-up. Let's see if I can get this where you guys can see it. I might have a better one. Yeah, this is not a good one. This is kind of a close-up where you can see it, but not very good. We'll find something better here in a sec. Okay, so this was me bringing my camera too close to the microscope screen. So not a lot revealed here, just a lot of pixels. Here we go. So after I cleaned it with the Spider-Man toothbrush and some alcohol, if you can see these two little wires. Now, you have to know that this wire is about as thin as a human hair, and there's over 8,000 turns of wire on this massive, on this little sphere. And so it's pretty interesting how I can just pull apart with little tweezers and find where the wires were severed during that arcing and sparking. This is under my magnifying glass this time. And so kind of giving you the view of the coil, how it's solid, the epoxy worked, and then the epoxy didn't work. The reason why it didn't work, I'll just share now real quick, is that the hole or the opening in the mold was too small, and so I ended up having to pour the epoxy at a much slower rate than I'm used to. And so what happened is that the epoxy began to congeal in spots, and then as it started to harden in spots as I was pouring it, it started having these kinds of gaps. So I should have had a larger orifice on top of the mold, and I should have poked an extra hole in it to allow air as I was pouring it. So you'd think pouring these a handful of times that I'd learn, but no, I'm still learning. I'm still a novice at this. And so here is what I attempted to do, what Nathan does with his Tesla coils. And I took the end here and I put it down the throat of the coil. You can see I drilled a big hole through the center. And this is what I ended up with. Now, if you look at the lower left-hand corner, that little arcing and sparking, it's not supposed to be doing that. This was after my repair. So that arcing, sparking is going to be the end of this coil, but you can see it's pretty interesting where this corona discharge, this violet colored plasma here, that's coming through the insulator. That wire is insulated. That wire here is only non-insulated down in the center of the sphere. And so it's interesting to me that there's a little bit of arcing and sparking inside of it, but it has this sort of trickling plasma here on the top, and this is again going right through insulator. This is not copper. This is well, it's copper, but it's heavily insulated, and so this is what's going on. Nothing, not as exciting as I'd hoped, but an interesting experiment. Here it is with see. So I tried to repair it with hot glue. Yeah, glue gun is my friend, but unfortunately, it's not strong enough as strong as the epoxy. So you see it; it'll still be breaking free and arcing and sparking here on the left lower end corner. But here's another angle. Again, it's going down the throat of the coil, and it just has this sort of plasma through the insulator effect. And oh, there we go. In the lower left hand corner, those flashes of light. It sort of reminds me when you see like the planet Jupiter, and it'll have little storms on it, and if they catch the photographs right, it'll have like a little lightning show going on, and so I don't know, it reminded me of that. It's pretty cool. Here's another one. I'm just running it through some testings that I unfortunately know are not going to do well because because of the arcing and sparking on the lower left hand. But you know, I'm going to fry it and find out, as Nathan says, and watch this. It's it's not good. We'll see here. So this was right before the time that I went and got my fire extinguisher. So there's not much video after this. This was the look on my face when I saw the fire. I know, corny. Oh, okay. So I'll show another video on that fire, but this is what I ended up doing with it. I was very upset, so I was determined to take away that charred part. Now, yes, I'm cutting through over 8,000 turns of 32 gauge wire. Yep, sweat and blood and tears into this, and now I'm basically just destroying it. But actually, no, I'm going to do some stuff with it. There's the top half. I took it on the sander and I just leveled it, knowing that I'm going to have to try to figure out where I can connect into this half of the coil. The top half is already connected, but how am I going to figure out? Normally, I'll replay this again. Normally, when my coils like this fail, I'll look into one of these exposed spots and I'll just like dig out with tweezers a little part, and then I'll see if it connects. And about 90% of the time, my approach fails. But that 10%, I'm able to actually find the right wire and try to revive the coil. This is what it looked like when I cut it in half. And this is what's really cool about this experiment. You know, I don't know if you guys feel this, but I always feel like a hand of God's blessing on my projects. And this is one of those where here I cut it with that skill saw. I then just sanded it blindly just to get it flat. I came into my lab, and there, lo and behold, is the perfect wire sticking out out of the hundreds of turns here per layer. And it was exactly the wire that I needed. So that's just, I don't know, that's just way cool. I heard one time that oh boy, the rabbis teach that coincidences aren't, coincidence is not a kosher word. And so this is one of those interesting coincidences. I can speak. So I connected that little tiny protruding wire. I connected the other end to my LCR meter. And here I have a reading, not my LCR, sorry, my multimeter. And it's 360 ohms. And so that's roughly what I expected. It has here on my LCR meter 516 millihenries. An LCR meter, if you can afford it, it's so worth it. It gives you insight into everything you're working with. So here I'm finding out the inductance of the coil, part of the coil. The glue gun is my best friend. Whenever I have a very, very touchy small thing to work on. Here I did some solder work on that little wire. I immediately glob it with the hot glue gun, and then I just hold it. Everything is used by the hot glue gun as a temporary one. It's quick, it's easy, and then when I want to do something more permanent, it just peels right off. So uh, my one of my top instruments I use is the glue gun. So here's the temperature gauge as what it looks like when I'm depressurizing, when I'm pouring the epoxy. So what I'll do is I'll go to the thrift store and buy different sized instruments. This large vase here, I'm using to weigh my epoxy to get ready to pour. So I use clear acrylic, clear glass instruments on everything. You get them for $1 or $2 at the thrift store, and you're set. This is the epoxy that I use. You have to use exactly the same proportions. And so I use grams, and usually I work between 100 grams of each to about 250 grams of each. It's about the maximum I use for a pour. Here's inside of my messy 5-gallon vacuum chamber. You can see that it's been used quite a bit. Just wanted to give you a little bit of step-by-step of how I do these things. And so what I'll do is on the left, I'll put the epoxy there on the left after being mixed for about 5 minutes. I hand mix it. I mix the sides, and then I mix the bottom, and then I mix the center. And it's very important that you spend a lot of time on the on the sides when you're stirring, and on the bottom. If you don't focus on the sides and the bottom, then you'll have an epoxy that never dries, and it's terrible. And then you see on the right, I have one of my molds for a sphere that I'm going to share with you, another sphere. And you'll see how I have the wire here protruding. And then this hole here worked for some of my experiments, but for some reason, this hole is too small for my other molds. So I'm going to change this setup. That's why my polycarbonate sphere didn't work so well. Something worth noting, when you use the temperature gauge for a vacuum chamber, this is filled with vacuum pump oil. So you have to make sure that it's filled with that clear oil all the way to the top in order to get an accurate reading with your with this device. So I pull this plug out when I'm taking measurements, and then I put this rubber plug back in, and then I'll look to see if it's full or not, and I keep it full. So this was my epoxy attempt with that smaller sphere that I'm going to share with you. What's interesting is that this is a very small sphere compared to my Death Star. This is probably 2 inches, 1.5 to 2 inches in diameter. And yet I was able to get a smaller gauge wire, a 34 gauge, instead of a 32 gauge like the Death Star. And I was able to get the same number of windings I was able to get the amount of coiling to equal the same resistance and the same inductance as the Death Star. And so that's fascinating how you can just add turns of wire and yet keep the same values, even though the geometry is very different. Here I'm looking into the vacuum chamber, and if you can see here, let's see if I can zoom in here. Oh, I don't think you can zoom in on videos. So you can see the bubbles there. So as the chamber becomes more and more vacuum, it just pulls all the bubbles from the 2-part epoxy. I'll do this a couple times, and then I'll pour it into the mold. And then when it's in the mold, I'll do this again a couple more times. You have about 45 minutes working time. Once you get to 45 minutes, you're done. You have to be done in 45 minutes. Not sure what this slide is for. Oh, these are my AirPods in the middle. And this shows you how small the sphere is, the black sphere. That's why I did this. And there it is, getting ready to go in the vacuum chamber. Hot glue is my friend. So I just sealed the bottom, hot glue. There's a side view. Has 475 ohms, which is about the same resistance as the Death Star. I know the epoxy looks terrible, but this is what prototypes look like, I guess. All right, again, a close-up. So what happened was, because this was such a poor epoxy pour, I had to start grinding into the sphere to look for wires that were conductive. And so I just took it on the sander. I would sand a layer away. Nope, no good wires. Take it on the sander, and it's not a great process, but it's how I get my coils back in action. So now I'll sand them, or I'll use my torch. Then I'll put some solder on them. This is what it looks like as I'm grinding and taking it apart using the heat gun, sanding. Oh, that's what it looked like when I wound it. It's so pretty. The epoxy. I need to learn better. Here are the millihenries, as I shared. These are the same millihenries roughly as the Death Star. So that's the inductance on the the inductance on the sphere. There's when I cracked it open and I was not too happy. Here I am cleaning it with alcohol. So what I'll do is I'll sharpen some copper wire. I use copper for my points because there's a lot of free electrons in copper. And so I just feel like it changes the plasma display. People will use other items, usually a harder metal like steel or something, or use like a needle that's made out of steel. I've always used copper. So here I just sharpened some copper wire, soldered it, and then I use this toothbrush with alcohol. I clean everything with alcohol. It's the great part of alcohol is that it evaporates completely. So you can get back to what you're doing once you give it an alcohol cleaning. And so there was the wire that I found on the left after grinding it, or I'm sorry, sanding it. Give you an idea of the size of it. Fits in the palm of my hand. And there's the little guy in action. I just put it in the center of the concave quarter pipe bowl that I use for my other coils. And I'm just getting a little close up, just starting to get this thing working. Yeah, it looks a lot like my others. It has its own distinct look. But yeah, she started working right away once I figured it out. Let's see. Here's another side view. So I'm really high tech here. I use a Scotch tape roll here as the base. But here's I'm giving it a little bit more current, so you can see how the plasma is a little bit fluffier, has those nice twirls and twists in them, kind of like, let's see here. Nathan's pointed out, I can't seem to capture it, but you can see how they're swirling, and they look like they're swirling in. So, and these aren't very loud. I really enjoy the aesthetic side of this hobby. I kind of hate to call it a hobby. Maybe I call it a pursuit. So lots of fun. So this coil I'm really happy with. It's really coming out better than I expected. The reason why I'm testing such a small coil is I'm going to wire another sphere this size, but I'm going to wire it in pure silver wire. I'm going to use a wire that's the same gauge, but it's going to be 99.9% pure silver, and yet it's going to have that enamel coating, just like this copper wire that I use, the magnet copper wire that I use, and then I'm going to run these same experiments and see what are the differences of using silver. Let's see some interesting plasma shots of that little sphere. Some more bubbles in the vacuum chamber. Apologies, my slides are a little out of order. So yes, don't tell my wife, but I use her batter stir sticks. They work best when mixing epoxy. Here's the pressure gauge. It's going in the direction of removing atmospheres. of air inside the plasma chamber. I'm sorry, the vacuum chamber. And when my things are going well, I'll get really close to this -30. And that's when the bubbles really start to come out, is when you get really close to this perfect vacuum here, which of course you can't get to a perfect vacuum, not with my setup. And then I have a high-tech method of testing the temperature of the vacuum pump. This way I ensure that the vacuum pump is not run too long and overheats. All right, so we're going to change gears here. I don't know if you guys feel this way, but since I was a kid, when I'd go into a Home Depot, or here in the Midwest, we have a Menards, which is just basically like a Home Depot or Lowe's. I always get this sense that there's so many raw materials here that there's just the possibilities are endless. And when I go down the aisles and I see the copper and I see the different kinds of metals and wood and acrylic, and I just feel like the possibilities are endless. And I get this little bit of enthusiasm. And so here is one of my trips of enthusiasm. I was Googling on eBay for thin sheets of mica, because I found that mica is one of the best dielectrics used in capacitors. And so what I found is that microwaves, the older microwave ovens, they use a mica, a mica covering for when the microwaves come out and they come through the magnetron. They'll go through this mica and then heat up your food. And so the mica keeps the food from splattering into the magnetron, and the magnetron can send its microwaves through the mica, because mica has these special properties where it doesn't overheat, but it's clear, it's transparent, and it has other cool properties that you might want to look up about mica. So I ordered a bunch of these on eBay. Here's a view. You can see how clear they are. They're almost as transparent as glass. So of course I have my alcohol out. I'm gonna wipe them clean. And I purchased a reel of copper tape, just plain crafting copper tape. And I measured the copper tape to cut it in squares to fit on the mica sheets. So here's what it looks like. I don't have a very good hand at crafting, but these look pretty good. And then I place on each side of the sheet of mica, I place the cut copper tape. And so I know you guys can see where I'm going here. Yes, I'm making a capacitor, high voltage, high frequency capacitor. This is version 1. I'm going to be sharing version 1 and 2 of my capacitors in this presentation. I'm working on version 3 with that, which I will share with you guys in another presentation. But here I just took a little piece of wire. This was some crafting, the thinner reel of crafting copper tape that I took from my wife's crafting set. So yeah, don't tell her about that either. And so I'm using that copper tape to affix the wire to one of the plates of the capacitor. And here we go. We have, if you look at my LCR meter, we have 279 picofarads for this crafting makeshift homemade capacitor. Pretty cool. So I'm going to decide, or I've decided I'm going to make a bunch of them. This didn't come out too well, but I thought it would come out better. But there's some fractal designs that come up on the copper tape as it's affixed to the mica. So fractals are everywhere if you're willing to look for them. Again, you can see some. If I should have zoomed in better. I should have used my microscope. I'll do that next time. But there's these little branched out, almost like plasma fractals in here. Pretty cool. Yeah, another poor photograph. Okay, so this Shows you how I just hand peel off the copper tape. Nothing fancy. It's nothing pretty, but it works. So one of the things about improving the capacitance of these homemade capacitors is that the plates have to be the copper plates have to be as close to the insulator in the middle as possible. And so I bought these clamps here on Amazon, and I bought these acrylic sheets. And so I'm going to flatten these guys out to really improve the capacitance, um, move them from picofarads to nanofarads. Another picture. That's a better shot. You can kind of get a picture there. So here, I took and built 10 of them. And the red wires and black wires are only for to show a difference in the wires. This is non-polarized, so there's no positive or negative. Both can be either. But here I built 10 of them, and then I put them in between these acrylic squares. I then put them here in the clamp, and this is where the capacitance improved drastically. Almost doubled the capacitance by just clamping them together. Another view of it. You can see how the wire has just been flattened out as I clamp down, tightening the clamp. Another view of it. All right, so I'm going to now connect these homemade capacitor bunch here. I'll call it a capacitor bunch. And I'm going to see if it will give us some plasma, see if they really work. 2.5 nanofarads is what I was able to get best from these capacitors in the bunch. All right, so there they are connected to the ZVS circuit. It's time to give it some power. And look at that. Look at that. Capacitors are everywhere. I'm telling you. Some conductive tape and some insulator, thin insulator. And look at that. I mean, it's not the best plasma discharge, but for my first capacitor, I am excited. So yeah. All right. I think that's a duplicate. Yeah. Out of order. The duplicate. Sorry about that. These are before I put them in the clamp. Wow. Sorry, I got some duplicates here. Let me get through this. On my fluke meter, I was showing 3 nanofarads. I should have turned this. So you can see how I laid out the mica, and I was pulling copper. I was mass producing these basically, or assembly line producing them. It's probably a better way to say it. So one of the properties in the mica that I thought was cool is that it would bend the light into different colors. Now, these colors aren't pigment. They're just the way that the inner fractures of the mica stone and how it bends light. And so there were some pretty colors to be seen. So I thought this would be cool to share with you guys. Yeah, mica's a pretty cool stone. It's a pretty cool stone. Has a lot of history, I think, too, with Native Americans using making instruments from it. I'm sorry, not instruments, tools. There's another picture of the mica. More of what I used to create them. There they are as they're getting done. Okay, so this is my version 2. Instead of soldering wires, I actually cut strips of the copper tape and then placed them on opposite sides. And so then I was to stack them and hoping for a better result. Oh, this is something that I wanted to share. So you know how I was sharing that capacitors are everywhere? Well, I had some conductive aluminum tape. It was for the ducting for our washer and dryer. And so I thought, you know what? I'm just going to peel it off. I'm going to fix it to another piece of aluminum tape. Not perfect. And let's see what happens here. I'm gonna hook it up to my LCR meter. All right, and see what we get. Look at that. We are getting, oh boy, look, it's climbing. We are getting capacitive readings in the nanofarads. Now, that's amazing to me. It's absolutely amazing. There's no false readings. There's no what is it? Parasitic capacitance somewhere in my bench. No, this is just two pieces of tape, and I hope I have a video on it. But I do hook it up to the ZVS coil, and I can get some sparks out of it. But isn't that amazing? How just capacitors are everywhere if you're willing to look, just like fractals, right? So this was the settled down version. If you saw earlier, it was climbing and changing values. That's because my hands were moving. But I actually soldered just each end of that aluminum tape. And so it's actually coming out to 1,532 picofarads or 1.5 nanofarads. All right. Let's see here. I'm trying to think of which coil here I'm showing. So there I'm using my infrared camera. Oh, okay. So I'm showing you what's hot on the infrared. That's those diodes I shared with you. And here I'm just testing that small sphere. And so we've seen this guy before. Some really good discharges. Yeah. So it's interesting how the voltage changes. It doesn't change the length of them. They're pretty much the same length and diameter. This discharge, but adding voltage just thickens them up, which is really interesting. You would think adding voltage they would get taller or bigger or increase in diameter, but they don't. They just get thinner. There's a top view. Gotta love the top view of these sphere coils. My camera is very close too. I think these spheres use the electricity efficiently. So in one of the chats, someone asked if I ever hook these up to ground that's directly above the coil. And I shared that I hadn't. So this is just for someone's request in the chat on the last presentation. And so I'm just turning up the voltage here. And as I increase the voltage, it's getting that like thick yellow sort of hue to it. And you can see then as I decrease the voltage, it comes back to that whitish violet. So, all right. So yeah, this is what it looks like when it's directly over. And that is connected to ground, that opposite end there. Okay, so I'm going to be in some miscellaneous territory. So when you're building your whatever you're working on, it's always nice to have some clear sheets, like some plexiglass sheets, or sometimes you'll just want some nice thick plastic sheets that you can cut. And they sell these white sheets of acrylic on for crafting and stuff. And they're like $20, $30, $40 for a sheet. But if you can buy the same stuff, the same dimensions practically, but it's a cutting board, and you can get it for $7 or $8 on Amazon. And so just to kind of give you an idea that you don't have to pay the high price for your needs and your inventions or prototypes. You can just use the cutting board plastic, and it's just as good, and it's a lot cheaper. See if there's some more miscellaneous. So I'm just doing some experiments. Here, the sphere behind it is not connected to anything. And so this is just picking it up from the air. I thought it was cool to share. Yeah, the sphere in the back's not hooked to anything. It's just literally picking up the inductance, the radiant energy from the cylinder in the foreground. Pretty cool stuff. All right. This is I'm working on a stand for the small sphere. Once this stand is tested, I want a fancy stand for when I print and wind the silver sphere. So I'm just kind of playing around here with different designs. Okay. So the Variac does not report accurate voltage. It just doesn't. So here I'm running these coils, and on the left here you can see the amperage, and on the right you can see the volts. These are more of an accurate reading. So in the past I've said, hey, I'm putting in 55, 60 volts. That seems to be the range that I work with. Actually, it's 30 volts. So here, we're getting kind of a 30, just, a good sized plasma display. But it's running, as you saw, 6 amps and about 30 volts. I'll confirm it over here again. Yeah. So 30 volts and 6 amps. So this was really good for me, because I have to go back to the drawing board and change things. I thought that the voltage was much higher. So this sort of set me straight, and I no longer trust the Variac. All right. I don't know. Every hobbyist should have a thick super glue and a thin, but I wish. So I'm kind of sharing the things that I wish I knew when I started the hobby. So if you guys are getting into or just starting, these are really good tips. I hope that help. And we're almost done, guys. You guys have been very patient. My presentations do run long. Let's see here. Yeah, sorry. Not sure what that is. Okay, so the ZVS circuits that I'm using, that you'll see in all my displays, they are from a YouTube channel called Schematics. So you would just write out the word schematics, but at the end, instead of CS, that you would add an X, an XS, schematics. And so I use his boards. He designed them for induction heating. So I basically redesigned them for high voltage plasma. So there are also 2 other YouTube channels that have posted their designs of ZVS circuits. So on the top here, there's SciTube and Archangel. This is one of their designed circuit boards that they use for their ZVS Tesla coils. Then at the bottom here, it says Easy Project for You. That's the YouTube channel. And this guy actually offers his printed circuit board for free, the Gerber files for free, not the boards. And he uses these for wireless energy. So whenever I see somebody offering the Gerber files for ZVS, I'll just download them and then upload them to PCB. I use JLC PCB. I upload the files. They send me the circuit boards within a couple weeks, and they're only like $1 or $2 a circuit board, so good price. I put the sandpaper on the copper and drill it, and that's how I get my points. Okay, almost done, guys. So I like to put things on top of my Tesla coils and to see what they do. Here, I wanted to see how the fields were, where they had density spots. And so I coiled these LEDs and was trying to see where the fields were more intensive. And I couldn't really derive anything from this experiment other than that it looked pretty cool. Okay, let's see here. Okay, for MOSFET ZVS. Oh, okay. So if you can see in the background there, there's a fluorescent bulb. I took a thinner than hair wire and I connected the top of the Tesla coil and I taped it, or I connected it to about 4 or 5 feet away to a fluorescent bulb. This was, and for some reason, the wire was making these weird, I don't know what to say. It was waving in certain directions that was almost like a guitar string vibrating. And then here you can see that 5 feet away, it lit this fluorescent bulb. Yeah, I'm a wannabe Nathan here, but Nathan doesn't use the wire, so I got to do better. Let's see. Almost done, guys. It's always fun to just connect what you have in your bin of miscellaneous. Here's the audio transformer. I just hooked it up to the output, the Tesla coil. Thought it was fun. Yeah, so this transformer here, every primary and secondary wire was emitting plasma, which is pretty cool. I was looking for some sort of magnification. So I was hooking it up to the primary coil, and then to the secondary coil, it should have had some sort of step up. And so I was kind of looking for it to be bigger on this side than smaller, but ended up just being a fun experiment. Let's see. No, this is not the one. Sorry. That's a duplicate. Apologies. This is, I think, another duplicate. So that's the homemade capacitor. All right. So a friend of mine, he's an older gentleman. He's in his 90s. And he gave me his 1940s Van de Graaff generator. This is about 4 feet, 3.5 feet tall. And I've measured static electricity volts, lightning bolts, 12 to 18 inches. This thing is very powerful. So I want to incorporate these into my plasma experiments. I want to start combining these to see what kind of effects I can get. And so I'm going to get this thing cleaned up and running, and then it'll be joining my coils, and I'll be sharing my results. Let's see. I'll share this next week. So this is what 5 pounds of 99.9% silver magnet wire looks like, where FedEx dropped it and it came apart. So yeah, this is 5 pounds of silver. I'm going to be using this wire in future experiments. And yes, it's not cheap, but I think that it might show some interesting results. And so I just want to show that to you real quick. What I'm going to be winding with that silver wire is I'm going to wind a sphere. I'm going to wind a cylinder, and then I'm working with a friend who we're going to put out a cone. So I'm going to have a cone, a cylinder, and a sphere wound in 99.9% pure silver magnet wire, and I'll be sharing with you guys the results of that as soon as I get it done. And that's it. That's the end of my presentation. Nathan?
Yeah, I'm here, man. That was really awesome. Bring everybody back to the stage here. And there we go. All right.
Yeah, he deserves an applause.
I appreciate that. Thank you.
Absolutely.
My favorite was those little LEDs. It looks like a snake coming up and it's hissing out voltage.
Awesome. Thank you, guys. I appreciate it. Thank you for being patient. These can go long.
Worth it.
Awesome.
Yeah.
Look at the spheres. I'm glad you have trouble with your spheres too, Shawn. Wow.
You're tough to hear you, Ian. Are you close to your microphone?
Oh, really?
Oh, that's better.
Hang on, I'll just try and put my mic up.
Well, again, I just want to thank you guys all for listening in. I just wanted to ask real quick, are you guys, what do you guys think of the sort of step-by-step in-depth that I'm doing on my builds? Is that going too deep, or is that giving some helpful tips on how to build these things?
No, it's really helpful.
Yep. I think it's good. If I
Okay.
could get that in depth with mine, I would. Good job.
Appreciate that. Thank you, Gerald. I'm just tickled pink. I look forward to this every week. It's the highlight of my week. Thank you, guys. You guys are a big encouragement.
Thank you for presenting and sharing. What
Yeah.
you always have some really great stuff.
Yeah, thank you for being an experimenter and putting it out. It ain't easy to put yourself out there. I get laughed at all the time, but it still ain't easy to put yourself out there, right? It's
Yeah.
one of those things.
That's
You make a good point, Gerald. It's why they call artists brave. It's just because they're putting their heart out there. It's not just, paint and canvas.
I agree.
Yep.
So I hear Ian has something.
Hey, Shawn, can you guys hear me okay now? Is that better?
Yes.
Yep.
Yeah. Okay. All right. Cool. Yeah, Shawn, I was looking at you with your epoxy issues.
Yes.
Mine never made it out of the mold.
Oh,
It's not a bomb. Yeah, I don't even dare try to take it out. I had 3 epoxy attempts. I didn't use glue, and I used tape around here, but I
Yes.
wanted to have a hole. I wanted to have a hole on the top, so
Okay.
I got one of the black straws for the posts on the flat winder, and
Yes.
I put blue tape on it, and that worked perfectly. And I put one
Yes.
on the bottom end as well, and just drilled separate holes for the wires to come out. And
Looks amazing.
I had only a very narrow input for the epoxy, but
Yes.
I hadn't realized that when it was sitting in the vacuum chamber, all the epoxy started to pour through the tape at the seam of the former.
Yes.
And I couldn't figure out where it was going. I thought, I'm sure it was full. Why is it not full anymore? So I had to make up 3 separate loads. And
Oh,
eventually I
no.
realized I had all this sort of kitchen towel at the bottom to catch any drips, and I hadn't realized that it was just sodden with epoxy. And
Oh, no.
yeah. So, but eventually I let the bottom half harden, and then I poured in on top, and then I learned how to really properly evacuate all the air from the epoxy, and so I have no
Awesome.
idea what this will do. But it's almost full now. I have just a little bit more to go into the top, but I got caught up
Nice.
doing other coils and stuff. So yeah. No. Well, thanks for all the tips, Shawn. It's really good to know all this stuff. I mean,
Oh, you're welcome.
if you don't have
Awesome.
if you don't have the details about the builds and what goes wrong and what to avoid, I mean,
Yeah.
you end up reinventing the wrong wheel all the time until you can figure out, I see now. I see. So
Right.
it's great.
Right.
All that information that for me definitely is great. Yeah.
Thank you
Very
so much.
helpful.
Awesome. I can't wait to see it with electricity going through it.
Me too. I've got the ZVS board done, and yeah, I've been trying to build a few circuits, and I haven't been terribly successful, I have to say. I mean, they look great.
yeah, don't they all?
That's right.
Yeah, that's how it was for me.
I know. It
Looked awesome.
but look, I mean, whoop. I mean, I thought this was pretty
very
nifty,
cool.
and that
That's right.
the positive impulse side worked, the negative doesn't.
Hmm.
I actually
Wow.
rebuilt it. I thought, oh, okay, because I didn't have all the information from Gerald on the coil, the circuit build. So I thought, all right, I'll give it a shot with ChatGPT, and that's
Oh, wow.
so I rewired it all according to its specifications, and I thought, oh, excellent, right, this should work really well. Check on. That's an evening. That's an evening I won't get back. That's for sure. But I've rewired it again.
Oh,
But,
Chat GPT got you again, huh?
Yeah.
Yeah.
It's incredibly. It sounds so completely plausible and everything. It says, oh yeah, it works out this way, that way, that way. That's how you get the positive impulse. That's how you get the negative impulse. And you
Yes.
think, yeah, that all makes sense. Yeah.
Right.
Anyway, and then I told it didn't work, and it says, well, you must have done something wrong. You've obviously got a connection wrong.
Yes.
Yeah, it's never
Yeah.
Chat GPT that could be wrong, right? It's a
No.
lie.
Right.
Oh no, it's been wrong plenty of times, and I've pointed it out, and it says, "Oh, thank you for the correction." But anyway, yeah.
Wow.
Oh yeah, you gotta watch it with that chat AI.
Yeah,
For
that's
sure.
right.
Well, it just depends how much time you have to spend on this stuff, you know. So you want to
Yeah.
be trying to get things, trying to get that. Oh, look at that
Oh,
printer! Is that the
Hey,
printer?
get there.
Oh,
I
he
just
got
got
it.
it.
Excellent.
Yeah.
Nice.
Just got it.
So
Sorry,
you
I
got
didn't-
something to share, Ian.
Oh, real quick, Sean, that's what Sean chipped in for is the shipping, guys. So make sure you
Thank
say
you very
thank you
much,
to
Sean.
Sean.
Yeah,
Appreciate
thank you,
that.
Sean.
Oh,
The-
I
sure.
haven't even
Big-
opened the box yet.
Yeah. Well
Oh,
done.
good.
Yeah, we really appreciate it.
Well done. Well, Nathan for
Sorry,
supplying the
Ian,
printers
didn't mean to
as well.
cut you
That's
off there.
really good. No, not at all. That's good news. I use mine for everything all the time. It kind of runs most days, just doing stuff.
Yes. Me
Nice.
too.
Building stuff like this. You know, just all the formers for the toroids. I couldn't get the dimensions right, proportions
Well,
right.
I've been
and that's
having
a help
fun
of
with it.
printer, so.
Yeah.
Oh,
Yeah,
you've
Ben's-
been using yours?
Yeah, it just started working. We just printed our first component. Where is it? The stand, the first part of the stand for the V-gate motor. This is probably going to be needing reinforcement and adjustment, but the drum itself is the most important part. And I found a 3D part for that, and just going to fit some magnets in and see if we can drive it with the rodent coil. I have a couple ideas on
Nice.
how I can do that.
I can't wait to get started.
cool.
The stuff I'm gonna build.
Yeah,
We're gonna have some fun.
I'm
Make sure
excited.
you check through the box, Gerald, because I hide things in places. So in your little filament roll, you'll find a mini micro SD card.
Oh, okay.
So make sure you look for that in there.
I
And
will.
then the other part, like I told you, those pieces of cardboard that look like they're just cardboard.
And then there's a plate in there. Yeah.
There's a plate in there, yeah.
Yeah.
So there's little parts you gotta look around for, but
I look forward to cracking it open, to be honest with you. So I gotta print a little fin for my remote control helicopter that broke off the back end of it.
oh,
Oh,
It's like
nice.
one of the first ones that ever came out. Doesn't even have a camera.
you may need a smaller head because it's got a 0.4 nozzle. You may need a 0.2 because those
I'll
things.
order one if that's what it takes. Yeah.
Yeah.
I'll get into all those details with you in the very near future, I'm sure.
You got
But I
it.
didn't want to take away from Ian, sorry.
Oh no, guys. I mean, I've built your new one, and I've just been test driving it while Sean was presenting and trying to get it to work, and it's not working as I expected. So anyway, but I
The
do
new
have some.
coil?
I do have some stuff to show.
New coil or new circuit?
Oh, it's all kind of connected up. Yeah, new coil. This is a new coil, and I was
Oh,
just
that's
trying
beautiful.
to see. Ooh, that was getting warm. Hang on. I was,
Works
yeah.
of art.
but that's
Yeah, it's beautiful.
that's the that's the circuit there. Can you see it? Okay.
Yeah. Yeah, that's gorgeous.
Well, I actually included your maglev switch and potentiometer on it, but I haven't fully included them in the wiring underneath because I'm still working off what you were sort of saying in your acrylic presentations and just
Yeah.
pointing to wires and stuff. So it's easy to get it wrong.
Now,
Well,
Ian,
if-
hold on.
I'd
Joe?
also love to know your horizontal deflection transistor circuit.
Yeah.
I've got that built, but I can't get that to work either. So I've obviously not got the coil connections quite right because I think the coil connections were missing off that video. But
well, we could go over that.
for it. Yeah, that'd be cool.
Just so you know, Gerald doesn't write his circuits like everybody else does, Ian. So when you think it's a positive circuit, start thinking of it as a negative circuit and run it backwards. Okay.
And inside out.
Yeah, inside out. I'm telling you right now, he'll have you
Yeah.
guessing for weeks until you figure out that he's running it through the negative instead of the positive on everything. So instead of using a PNP like normal folks would, Gerald uses an NPN and runs it back
Wow.
through negative so he doesn't have to use a resistor.
Wow.
It's like allergic to them.
Ah, well, yeah,
That'd
but
be-
I'm using Gerald's positive pulse circuit, the basic one that I was getting the results was on that coil that I showed. That is showing definitely positive pulses going from the seeing on them on the scope. They're
Yep.
they're positive pulses, no matter how you dress them up. Actually, I tuned that for the best output from the solenoid coils as opposed to the best performance of the coil itself. Just
Yeah.
and it's just measured, just looking at the voltage on them, kind of thing. So
That's awesome,
yes.
man. Yeah. Yeah,
Well,
I
anyway.
do things differently. Like Tim Johnson said, sometimes I put these in my circuits and I shouldn't, right? So, but yeah, I run my circuits differently because I wanted to be able to control the system through the load, not through the circuit. So,
Right. I know I've got two cat banks here. I've got halogen light bulbs, stuff to act as a load and put them in parallel and stuff, but the circuit's not working right. I didn't finish the new coil until this afternoon, so I've been rushing to get everything assembled for tonight, but it hasn't been very successful on that front. But at least I can show what happened before and what I've changed in the coil this time. This new coil, Gerald, is a bifilar version of that one that I showed. So
nice.
it's entirely 180, but two separate coils laid on top of each other. So yeah, I just measured the inductance on them, and one is 1.2 millihenries, and the other is 950 microhenries. Yet they're exactly the same length. They're just going in opposite directions, and I know I didn't make any mistake. So that's kind of
Funny
strange.
how
Is
that works,
something?
huh?
It's because you have two coils, you're getting an inductive effect because they're so close together.
Right. But why would they be different? Because you think if you measured the inductance of one, then it would be this one, and then I go to the secondary coil, which is exactly the same length, but just in reverse. So I'm going into the so maybe if I I maybe should just reverse the input and output of the second coil so that it matches the first, and then
I was just about to say, when you're measuring it, you got to understand the measurement tool only goes for that positive. It doesn't really see the negative rail properly. So if you reverse your leads, you might get the exact measurement.
How far are they off? What are they really off? Or
not much.
Well, 950 microfarads compared to 1,195.
So 200 microfarads.
250, just about. Yeah. 240. 240 microfarads, which seemed a lot.
Yeah, interesting.
What's your ohms on them? Have you checked?
No, I didn't. Oh,
I bet you it's low.
No,
That'll show you how close they are in length and everything.
Right.
Okay, so you know a lot about that, Shawn, right? When it comes to resistance of a coil, let's say 750 feet.
Yes.
What would that average for that be? Do you know? Because I only have. Go ahead.
So if you Google the wire gauge and it ohms per 1,000 feet, and then you can just do the math because it'll tell you the ohms per gauge wire.
Right.
And so then it'll tell you, because I use that. I'll measure the ohms, look up, okay, I have 32 gauge. It has 20 ohms per 1,000 feet. And then I only have 10 feet. So I figure out how many ohms per foot. And then when I take the reading, I immediately know the length. Does that make sense?
It does. It does. I'll try that, but I get anomalous readings, and that's why I think that Ian, his ohms are going to be very low. I mean, I have 750 feet and I got 6 ohms resistance.
So also too, when you're measuring ohms in coils of wire, it's very temperature dependent. So if it's a 10 degrees difference in your room, you'll be surprised. You'll lose an ohm or you'll go up an ohm. And it gets worse as you get up in the higher ohms. So just so you know, it's not like a resistor where it'll keep its ohmage value.
Right.
Wire is very, it interacts with the environment more.
That makes sense. That does. Thanks for that. Ian, did you want to?
Yeah, I could share some stuff with you. I will try to present something here.
Okay.
Ooh. Okay, can you see that?
I don't have anything yet.
Yeah, not yet.
My screen, there we go.
There we are.
You seem to be going into the distance. Yeah, can you see that?
Yep.
Looks
Is that
great.
good? Oh, okay. All right. So this is so I haven't been completely idle. I know I've been busy with work and all kinds of stuff, but up here, that's the cornea coil from the experiment I uploaded to my channel, basically based on that coil. And this is the one I completed today. It's bifilar version of that, but I also added the pentagram because of some information I came across recently, which suggested that that was the third of the major third in the triad, which I didn't have. I only had the fifths and octaves before in this coil. So I wanted to include that. This I only had, I think, 6 of these before. I've now doubled it up to 12 so that I can put 4 sets of 4 pairs on the outside. It's very strange. I mean, I could show you when I show you the video of this one. Hang on, am I talking to myself or are you all hearing? Okay.
Nope, we can hear you.
We can hear you.
Okay, great. All right, cool. Sorry, I've not done this before. So basically, it's very strange. I put one of these inside here when I was just running your basic positive pulse circuit, Gerald, and it worked. And I turned it upside down, and it did nothing. So it was orientation dependent. And now these are 5 layers of 140 windings of 20 gauge wire directly put onto antenna, what do you call it, ferrite rods.
So it's like 500 per coil or
700 turns per coil.
okay, but it's only 140. Go ahead.
Pardon my French, they're a bastard to make. I mean, your hands are really sore at the end of it. Because you've got the antenna rod ferrite ends are the ends of the coil, so you can't use a winder with them, so it's difficult. So
what are the dimensions?
They are 14 centimeters long. You know what? I know we're in America. I'll try again. Where are we? So if I can find a ruler. Oh, yeah. Okay. So 14. Basically, they're about 6 inches long, just under 6 inches long, and you can gauge the rest off that. So so they're 6 inches is about 150 millimeters. So they're 100.
Yeah, they're just regular ferrite rods.
Yeah, just standard ferrite antenna rods that I got for I think I got them years ago for the tiny generator. I seem to remember the solid state version of it, but I'd never made more than one. When I saw another review, I thought maybe this isn't worth it. So so I had to make another 7 of those before I could continue with the experiment. And then I wanted to wind this new one before I did that and use a different circuit. So I've kind of convoluted myself a little bit. I really wanted to complete the one coil that I'd made with its configuration and see exactly how many solenoids I could get useful voltage from, and then see what happens. But it's interesting. I'll tell you what. I'll show the video again. I know you guys have seen it, but maybe not everybody who's watching has seen it. I'll show the video of how this coil behaves,
Please do.
and then talk about exactly where I laid these and what orientation I put them in, because it was different outside. What would work here would not work here, and what would work here would not work here. And everything that worked was in the gap. It wasn't against the wire, it was in the gap. So that led me to, so this coil is a solid former with a framework inside, whereas this new one is completely hollow. So I can drill in through the gaps and put in and check the magnetic behavior in there and other stuff as well, and just to see what's going on, because everything was at these gaps here all the way around on this coil when I tested it. So and the coils were joined in series in the center. You put them in parallel, nothing happens at all. They have to be in series, and they have to be opposite in polarity, in I guess polarity, and then the other two have to be reversed of that again. So it's like two pairs, but they're all in series. And then I got maybe an extra 10 volts when I put a third solenoid, so you had 3 on the outside, but so it wasn't worth it. So I ended up with pairs, and the pairs worked fine. They were giving like 50-60 volts, and there's room for 5, but I kind of ran out of ferrite rods at 12, so that's fine. I thought, okay, I've got 4 in the middle, and then I've got 4 sets of 2 on the outside. So I've yet to do that experiment with that. I just wanted to have a look and see how this one was behaving. So so that's basically those. Then Shawn, there's your bomb. It's more like a Christmas pudding or something, I think. But anyway, I'm not even going to dare try to take that apart, because I know there's sealed epoxy all the way around the center of the mold. And I got a lot of air out. And when I did the second epoxy run, I frothed it up in the container, and I put it in a bigger container to froth it up further. And then it stopped overflowing. So then I could, get it. And then it was much better quality epoxy went in the second time.
If you want to be able to take off that is that PLA, what's the outside?
It's
Filament?
PETG.
Oh, PETG. Okay. Yeah. The secret to getting that off is just use a heat gun. The epoxy can take the heat, but the filament can't.
That'd be good.
Oh, right. Okay. And then I can see what's really going on. The only problem is that the epoxy has actually set around the conductor's top and bottom, which I'm not sure what to do about. So
I know where I've seen that before. Donkey Kong. Sorry, I had to.
I know. Yeah, really. That's exactly
it's awesome. Really, it really is. I'm just.
That's awesome.
Yeah. But look, it has its own stand now and everything. So, and I can actually look inside it, because the straw did its job perfectly, and the whole inside is empty. So I can actually put probes down and wires down like you were doing, Shawn,
nice.
and take a look and see what's going on. I mean,
Very
I
nice.
do, yeah. Now these coils I made, anyway, I can come to those later. I've got to I can move on here for a second and see. Right. So these are the Egyptian brazier, as I call them. They look like Egyptian. Right.
I have a dirty mind. I'm sorry. I giggled to myself.
But hey,
now we all know what you see there, Gerald.
No, he sees lots in that. Yeah. Gerald is very anatomical circuit diagrams, right? But anyway, but if you notice there, Sean, that's the formers I sent you when I'd adjusted yours. Those
Yeah.
are, I had to do
That's
them in
lots.
quarters. I did them in quarters, and then those are two, obviously 4 quarters glued together, so that I could wire 2 halves horizontally, because you can't
Oh,
print them like
wow.
that. You can't print them like that. So I wanted to wire 2 halves, one clockwise, the other anti-clockwise, and have 2 separate coils. I'm not sure what to do in the middle, but I was thinking to put those primer bowls, those David LaPointe primer bowls inside these. So I'm creating
Wow.
a permanent magnetic field that's strong, but it's very directed and polarized because of the nature of the bowls. Just as
Yeah.
something interesting to do. There's another guy online who really works brilliantly with callback arrays and all kinds of magnetic using that same bowl, and also circles. He makes spheres out of magnets to see what the gravitational field is like on them. Omega ZZ, that's it. Omega ZZ, wherever you're from.
Oh, wow.
Yeah,
Interesting.
definitely have a look at his channel. He does incredibly complex and very, very analytic things with magnetic arrays when they're actually put together, and he shows exactly with using the color magnetic.
Yeah, he does a good job.
Yeah, I don't know. Have you seen it, Gerald?
Yeah, is it the guy that has all those little tiny round magnets inside the bowl, almost like the primer fields?
Yeah.
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 Good channel.
And he does, Omega ZZ. So I've been very interested to see that, but I just have the bowls, and I made several of them for an experiment. So I thought, well, I might as well see what I can do with them. And if I don't join the coils in the center physically or glue them, then I can actually change the polarity of the bowls that I put inside them. But
Fascinating. Good idea.
Yeah.
I look forward to it.
But if you see, I mean, that's the PLA. The finish is not great. I got to do some work on those to be able to wind them properly. But otherwise, it'll take another 2 weeks to wind one. That's the longest coil I've ever wound, I have to say.
Yeah.
And there, that was
Oh, nice.
that was the finished version of it.
Yeah.
Very pretty.
It was, I didn't even think. I thought I'll make the hole down the middle. I'll make it 1 centimeter, 10 millimeters. That should be fine. And it just fit perfectly around the shaft for my coil winder, which I found out after. I thought, oh, excellent, right? So it doesn't move
Nice.
around, it doesn't jiggle around. So anyway, yeah. And again, I had to write the numbers as they were coming up, because they were changing a little bit from different parts of the coil. At the ends, either end, left and right, was a lot more. You could get a lot more winds on for some reason, and then suddenly it really shallowed out, and I couldn't get the same amount of winds on. So that's where you see sometimes I'm expecting it to fit, and it's not quite the same. But hey, 4,650 winds later, we got to the end. So
Awesome.
but I mean, look at the inductance there. It's like you got 653 ohms and 876. That's getting up on 1 Henry, right? I mean, that's huge inductance.
Yes.
So, yeah, which is incredible to think what could go on inside that thing. It's amazing.
A lot of magnetic energy storage.
Yeah.
Yep.
So and then, as you know, that's what we've ended up with just for now. But once I just need to finish off. I have a little bit more epoxy to fit in the top, because the third lot I made, well, I had to buy some more locally, and it set much faster than the other stuff. So by the time I de-aerated it in the vacuum chamber and tried to do it, it was slow, and the gap isn't big enough. I did bubble out everything I could get out of it, though, but I needed to start again with a fresh batch, so I ordered some more. It arrived,
Nice.
but I've been traveling and doing stuff and fixing hurricane stuff since I got back home. So there, and that's the top. and that's the gap I had to deal with basically. So it doesn't look good, does it? Globs on the top there, but anyway, yeah, it should be. Anyway, we'll see what happens. I'm optimistic that it'll still perform reasonably well.
It's good
But as I
work.
say, yeah, the heat gun
Yeah.
might work well for it though.
Yes.
But yeah, the things you can do with drinking straws, huh? Yeah. And then eventually, once I get it running, and I've got obviously your ZVS board is pretty much it's ready to go. That's just an arbitrary pair of capacitors there. I'll obviously figure it out. Your tuning method is excellent, Sean. Thank you very much for that too. That's really
Oh
useful.
yeah.
Sure.
Yeah, it's brilliant. Yeah, so I mean, I was able to. I've got the three the different pipe you suggest to get the thinner stuff, the thinner
Yes.
copper pipe. That is so much easier to work with, no question. That's
Yes.
nice.
It's
I
the
was almost tempted
0.2
to.
wire, right? The 0.2-inch diameter instead of the 0.25.
Is that 3/8? No.
Three,
Yes, 3/8.
5, yeah, 3/8. Yes, yes.
3/8. Yeah, there was 3/8 inch I got, and it's great. It's like refrigerator stuff, but it was so pliable. I thought maybe I'll put a primary inside this toroid coil I'm building, and I said no, stop. Got to keep the variables down because I'm trying to figure something out. So adding the pentagram to it though, that was I thought you shouldn't really do this, but I thought no, what the heck, I gotta try it. So yeah, something else I've been working on recently is this. This is a slide from oh my gosh, it was from the Tesla Tech, the rodent coil presentation. Phil Dubois, and he, you see, these are the rodent numbers, but this is actually mod 9 with the 3, 9, and the 6. Now, this is stuff that Marco Rodin found and discovered, and I think Phil Dubois rediscovered the, I think the top line. What is that? Let's see. That should be 3, 1. Is that it? I'm just looking to see. Yeah, 1, 1, 2, 3, 5. This is the Fibonacci sequence reduced to mod 9. The top one is 1, 3. That's the Rodin sequence. So there are the three. There's the 1, 8, the 7, 2. Sorry, 8, 1, 7, 2, and 5, 4. And those are all very intrinsic in the mathematical kind of theory about the whole of VBM vortex-based mathematics.
Is that the
Bottom one. Now
principle
this
you
is this one where it starts with 1, 3. Where is it? Yeah. Anyway, so this one is the Lucas sequence, which starts. I think that's 2, 1, 3 or something like that. I can't remember. I'm looking for it here. I should have annotated on this, but I forgot. But anyway, so you've got the Lucas sequence, the Fibonacci sequence, and there's a Rodin sequence, because there are 3 sets, and it's like a 3-phase system that actually works. You shuffle it around a bit, you can get it to start with 3, 9, and 6. So I'm trying to figure out a coil geometry in a geometrical representation of this that I could wind on a toroid as well. Because what he said, which really fascinates me, is this. This is another one of his slides. So what you have here, his theory is that when you look at the toroidal field, you have the 9 is the block wall. That's the plane of inertia, basically, where everything comes from. You then have the 6 and the 3. So this is longitudinal. These are the longitudinal pulses that come from the ether. The 6 and the 3 are the transverse mode of normal magnetism that forms around the 9, around the the null zone. And what he's suggesting is that the 124875, the kind of helical result, is a hybrid of the pulsing 9 and the magnetic 6 and 3. So it kind of made sense that if you're going to do that, you'd need to build a couple of coils that have, now that is 6 coils on that. These were actually originally for things that we're not allowed to talk about, of course. But the nature of this coil, it's counterwound. So you've got 3 coils going clockwise. There are 9 wraps per turn, all the way around. And yeah, the only way to do it is to use sort of like fast epoxy on these physical joins here. Otherwise, things just start breaking. But yeah, I was very pleased with this. I spent a lot of time and detail on this to make it absolutely perfect. Because but this one, all of the coils all start and end at the same place, except the bottom set go clockwise and the top set go anti-clockwise on top. But they are 6 individual coils in essence. So that gives me something to play with. But when I thought about it, I thought, well, no, if I need to separate the 3, 6, and the 9, I need to have them offset at 120 degrees apart. So I haven't had time to test this, but if you then start to use that inherent geometry within that, and again, there are 6 coils and they're counterwound going in different directions.
That coil's going to produce.
Yeah.
Sorry, I didn't mean to cut you off. That coil's going to produce because you put it 120 degrees out of phase, and it's that one 100, or there's 100. Each one's 120 degrees. But is there a bifilar in that, or is that a trifilar?
It's 6. There's 6 coils in that. There are 3 underneath and 3 on top, but they all start and end 120 degrees apart. So essentially, it's trifilar. Essentially, yeah.
That's going to produce.
Yeah. So I'm really interested to do something with that. So again, that was the first one I made, and the former I had wasn't quite large enough to get a nice, neat inside. On the inside diameter, it wasn't too bad. I think I just made one mistake in that, but it wasn't too obvious.
It's nice
at the time, anyway.
But anyway. So let me understand that your numbers are all based on Rodin's numbers, so to speak.
Not really. It's mod 9 is mod 9, no matter how you dress it up. It's
true,
it's everywhere.
True.
So I'm just trying to integrate that along with the music theory as well, in terms of, I mean, the reason I started this back in 2015 or 16 was basically I was kind of fed up reading about all this stuff and I wanted to really try and make something, but it was all based on the fact that a major chord, it sounds so pleasant, it must mean something deeper. That's been the whole impetus of what I've done, is based on I was a drummer in my early life, and I love rhythm, and it does something to me as well. So everything that vibrates and moves seems to carry significant meaning, because otherwise you would just pass you by and you wouldn't even notice, right? So anyway, so I'm trying to marry it all together in some way or other that actually makes logical sense. But I'm still really scraping around in the dark, to be honest, but I'm just trying different ideas. I'm just trying different ideas to see what we could do. No, Gerald, I'd be really interested. I'm all open to suggestions for what to do. I just need more circuits. I've been a uni circuit guy. In fact, I'll show you what I've been trying to do is I want to create longitudinal pulses, impulses, but without. I just wanted to try and avoid a spark, though that's probably ideal. And also, yeah, Gerald, those little gas discharge tubes.
Yeah,
I bought a bunch of different rated ones to try and to use to see if I could use those to pulse the secondary. I think you were doing that at one point.
Yeah,
that would create a resonance in the secondary around the primary to actually get different effects as well. And I was thinking of trying to include that in this, where I'm, I'd be pulsing
from one to the
I'm
other,
not quite
and then
yeah,
no,
and
that
trying
would
to
work.
get. Okay, all right. So that'd be interesting for sure. But
Can I say
but again, what's that?
watching your work, it's amazing. You're thinking outside the box, but still in the box of rodent, and you're still killing it. I love it. When I put my numbers in your hands, you're gonna surpass me, Ian.
Oh, well, that's cool. I mean, I'm
Like
looking
you
forward
have
to.
the mind for it. And seeing how many coils you've wound already, you have the bug. So just wanted to say
I
that.
do. Yeah.
Yeah.
All right. Thanks, Gerald. That's cool. Let's see. Oh, yeah.
You
Right. So this was an experiment I tried a couple of weeks ago. I've been in contact with Evo, and he kindly um, told me that he had an impulse, like a current impulse circuit together, and that's what's in the center there was the blue capacitor, uh, and the choke coil. It's basically there's that is not a transistor with the heat sink. That is a diode, but it's a thousand volt. I think 10 amp diode, MUR 8600 EG, I think. But anyway, but it was getting hot and the coil was getting hot. So I obviously connected the coil, the choke incorrectly, and I checked with him and he said more than likely. So I never got that finished to work, unfortunately. But the way I need to do it is to use a gate driver with the MOSFETs. And that's what this is, right? So I
Hey,
made
Ian.
this a few years. Yeah,
Ian, can you go
yeah,
back to that slide real quick? That rodent
sure.
coil on the left.
Oh yeah, yeah.
How many
That's
nodes?
that's one of 36. That's a
36.
36. Yeah. And it's also, but it has one nested inside it, and that's when Evo put his circuit onto his workbench.
Mm-hmm.
He showed that the two coils on the choke should be, I believe it was 10 microhenries, and it
Okay.
suggested that if you had a 100 microhenry primary, that would be ideal to work with it. It just so happened that the inside coil in that rodent pair,
Mm-hmm.
that's the same. Nathan, you'll recognize that. That's a. I mean, I was working in Guyana at this time, and when I made it, so that I could travel with it, and so I
Mm-hmm.
made a 50% version of that big one that I had
Oh, you
made.
did.
I think
That
years
it
ago.
looked like
Yeah,
it.
it is. It is. Except it has that nested coil, the phi ratio coil inside it. So when using that as a primary, I then thought, well, I naturally have a secondary already in place to test this circuit out, because I think it was about 8.5 microhenries, or 85 microhenries was the primary inside. I think it's anyway, but so yeah.
So
But
what are the
anyway, that
specs?
that was that was another that was another kind of failed experiment. But these boards are so powerful. I mean, one board, when they're connected up, those MOSFETs are in series. They both have an individual gate driver. I think if you could see them here, those are the gate driver ICs, and those, believe it or not, before they're soldered, are epoxied in. And yeah, that was my introduction to electronics. This stuff. And
Wow.
Wow.
Evo did. He
wow,
did help me a bit, but yeah, I learned how to solder doing these boards. But the boards were made, which made it so much easier than trying to build a fully fledged gate driver circuit from scratch. The boards were brilliant. This was his half bridge boards. So they were built so that one would pulse positive and the other negative, like in a push pull.
Hmm.
But you need a dual power supply for that, which is wired in series, so that you can get the individual outputs from both sides of from both channels of the power supply. but it's good. I mean, and it works. I mean, I no problem at all. 3,500 volt impulses, positive or negative, out of that. And I tried using a lot of the pancake coils before, and got. I mean, all the coils were exactly the same with different sizes, different get wire gauge, all kinds of stuff. I think but I could always see that it was purely inductive and there was no gain at all. It was as soon as you put them close to each other, they would change the power requirement. So there was no obvious gain going on, but the impulses were really impressive. So then I tried doing his coil capacitor experiment by actually firing two opposite impulses and then putting a DC offset both positively and negative on the negative and positive um, impulses. Um, but interestingly, I could never get those pulses to match up, even though they were exactly the same point. Even if I moved them around a little bit, the spikes of those pulses would not go together. They refused to. It was like I was trying to create an implosive effect, really, out of the center coil, or this space in between. But anyway, but there was a good learning curve, and they're still really useful for very powerful impulses. Thank you, Eagle.
Ian,
He's a really great guy.
Ian, what's does the wave look like when you say impulse? Like, is it a sine wave, square wave?
It depends. No, to get the impulses with these, you need two primary coils, basically. So if you use um, resonant L1. So the L1 and L2 are the two primary pairs, and the secondary would be the L3. So it uses the pulse from the first primary, which it then goes through the MOSFET, and then it either stops, or it either goes to a collection capacitor on the other polarity, or it goes straight into the L2. The L2 is then tuned with series capacitors, so you can get a really nice, and it's very, very efficient. There's hardly anything coming out of the power supply. I mean, you could be turning that up to like 20 volts and it'll be 0.0 something amps at the other end, for getting like thousands of volts of the impulse itself in either polarity, depending on how you wire it up. So it's extremely efficient and extremely good. It's just trying to adjust it to make it work optimally with coils like toroids and things is difficult, because you've got to have that extra coil. But the tuning of that coil. Oh yeah, sorry. The waveform, as you asked, is it's basically it's a spike, but it's in both directions. So it's a pulse, but it's not unipolar, and that's the problem. It needs to be a unipolar pulse to actually disturb the ether in one polarity direction in order to create the movement. Otherwise, you just bouncing it back up and down. Basically, you're creating a, and maybe if you had 10 or 20,000 volt impulses, it might make a difference. But when it's down around 3.5, I mean, I couldn't see any, and I know Evo was trying as well, but he couldn't see any major benefit coming from it, no matter how hard he tried. But anyway, so the waveforms are, if you have, if you tune like a very large, like say tubing, I mean, the impulse that's going into the secondary that is resonating with, or if you're resonating into the second primary, is probably about, I think last I saw he had it down, it's about maybe about between 40 and 60 nanoseconds was the pulse. So it's really fast, MOSFETs are really fast, obviously, and much faster than transistors. But anyway, so I'm trying to use this MOSFET driver board to drive that circuit of his to get the unipolar impulse, which would go from a positive buildup through the choke, and then he uses that to discharge negatively out the other side, and it is in one direction. So he says it works. I just obviously haven't wired it up right yet. But that's what I would like to do with the 369 and using that block wall idea of the 9 being the 0 point, and then the transverse mode would be across that. I'm trying to figure out a way to use this to actually create the longitudinal impulse and then apply the transverse waves to it to make this hybrid wave to see what happens.
Wow.
Hey, Ian, I got a question for you.
Sure.
Victor was asking, do you feel the coils or coax? I think he's looking at the two things that are coming out there.
BNC. They're there for the signal generator inputs to either of the gate driver circuits.
Okay.
So yeah, it just stops clips really, and it just makes setting up and breaking down easier. So that's why you see them in all the other stuff that I've been making. Is I use the BNC connectors the same way because they're easy, they're solid, they generally don't break. I've not had one break on me yet when it's put properly on the board. So, even the other sort of earth board stuff that we use, the TAN stuff.
Very
But
cool.
anyway, so those are 3 boards, by the way. Those are 3 separate boards. You can actually link them in series. The only thing that limits it is the IC chip, and for each of the these little things are good for 5,000 volts. But they separate out the low voltage circuit from the high voltage MOSFET circuit. So they're isolated gate drivers, but they can handle a 5,000 volt difference, as I found out when I blew all 8 MOSFETs in one go once. But I was up to 10. I was up to 10 kilovolts in using a couple of pancakes and secondaries and things like that, but all pancakes. And it was fun to do. It was even more fun because I think I was in Guyana and I could hear the breaker box in the kitchen, and it was clicking like crazy. And I had my current meter, and it was just red lining. And even when I put it into the next room around the wall, it was still red lining. So I had to turn it off to stop. So I don't know what kind of fields I was putting out with that thing at the time, but it was happening.
Probably.
But I stopped when I blew all the MOSFETs, and that was that.
You're probably
That's
feeding it
expensive.
back into the line. That's why it was clicking.
What's that?
Said you're probably feeding it back into the line. That's why your breaker box was clicking.
Oh, really? Yeah.
Yeah.
Yeah,
I got
Probably
I
as
got
well.
a
I
few
blew the
things to
MOSFETs
say.
then.
Your
Anyway,
presentation's
all right, so
awesome.
So this was this morning when I got up. I'd done three of the geometries, and I needed to do 2 more. So yeah, I still had a way to go. Oh yeah, that's a photo of the experiment that I was doing that I did the video on. Shall I just show that? I'm not sure. I hope I can share it.
You haven't shown the video yet.
Yeah.
Hang on, let me just. Do I have to hit stop sharing to go to share the YouTube link? Or
Yeah, you can go right to the YouTube link.
okay, right. So I'm not sure how to do that. Let's see.
You'd hit play on your video and share it that way, yeah?
Okay.
Or the YouTube
Well,
link.
there you go.
Yeah.
Well, maybe this should just work. I don't know if the audio comes through though, but just a good date on this. Can you hear it?
Yeah, coil. Yeah, so I've
You have
got some more
audio?
solenoids to go around.
Yeah.
They're all the same as the original one that I tested before, and there two are going to different rectifiers, and then being put into their 10 microfarad caps. And so the 4 in the middle are producing 200 volts at about 40 milliamps. The 2 on the outside, the 2 pairs, are actually showing 54 and 60. And again, there's 40 milliamps measured on that. It's using this, and I'm not sure if it's correct or not, the amperage. I'm just going with what it says for now. And so there are 3 separate pickup sets. There's room for 3 more sets of 2 on the outside, 3 more pairs. That would actually increase that. So you got about 230 volts, sorry, 430 volts there. That's for the power supply is only 12 volts input, 1.75 watts, and 24 volts on the square wave. It's 50% duty and 66.6 kilohertz. Gives these bizarre waveforms. The output from the coil is the top on the yellow. The amber is the base of the
Magenta.
and blue is the output of the 4 in the center. Just to look at the waveform, and the bottom is the current coming out of the coil, the center, the actual coil itself. And wattage, and the wattage for the signal generator and the power supply is 10.4 watts. So yeah, potentially more than that going on here. Interesting point is, though, that as I add the solenoid coils to the center, the power supply draw, it started, the control wattage was 2 watts, and it just gradually crept down as I entered more coils into the, and around this, into the torus coil. So that was kind of bizarre. So it's for free. Anyway, thanks. So
Awesome.
What was that?
That was really good.
You want
Yeah.
a bit
So
go ahead.
yeah, I remember you saying at the time though that it should work better, but it's a single filer coil.
I'm surprised you're getting that out of a single filer.
Yeah, but don't forget, I was winding backwards on the same wire, 180 degrees. So you would have just had a very slight timing difference, but
Yeah,
but obviously it's not 2 separate coils interacting. It's the same coil interacting with itself, kind of thing.
still interesting.
Which is why I built the one today that is bifilar proper and wind from 2 separate spools. Going in opposite directions. So, but yeah, just going back to the that experiment, what was the point? Oh yeah, and even the watt meter I had, I noticed that when the signal generator was just on standby, it was pulling 3.5 watts without really doing anything at all, and I didn't measure the power supply, so 10.5 watts is pretty excessive for what's needed, especially if you're using smaller things. But the main things that I noticed was that I could put an LED across the output of any of the solenoids or a group of them, and it would light up. And that was before the rectifier. So it was just the raw AC that we would know it as was lighting the diode, which means it's not regular energy, right?
Did you
And
flip
when I
the
put
diode?
An LED is a diode, and it was lighting up no matter what direction it was connected to those solenoid coils coming out. So, but that's before it was rectified. And even after it was rectified, where I first tried it, I could connect it from either side, and it would light up in both directions. So it was just it was taking energy through it. And then I also noticed that I should have taken a photo out. I need to dig it out. The original LED that I did an earlier experiment with, just with a single solenoid, is completely milky, pearly white inside. It's gone opaque from however it interacted with whatever was going through it, which is kind of weird as well. So, yeah,
Hey, it went
I
opaque.
have to break.
I gotta say
Right,
this. It went opaque because you were running the diode backwards from the regular energy. I've done it before. I know exactly what you did. Yeah.
Oh, okay.
Because
So
diodes are meant to go, like the LEDs are meant the energy to go one way, right? But this energy goes backwards. It'll go both ways. It doesn't matter. And when it goes
Right.
backwards in the LED, it causes issues.
Oh, right. Okay. Okay. So when you run your LED banks, you actually buffer it with capacitors. Is that right?
Nope.
Do you have capacitor bank in parallel for the
I
actual?
do. I have run that from the capacitor bank, but I can run it strictly from a coil from the inner core directly to
Right.
the LED bank, but it will only run one way if I'm only pulsing the primary. If I'm pulsing the
Right.
primary and the secondary, it'll run both ways. So the coil that you were running, because you wired it, even though it was single filer, you wired it 180 degrees out of phase, you could flip your LED.
Gotcha. Okay. Right. Then
There's
that
actually,
makes it.
you're there, Ian. You've got a few things. Okay, so I've been writing down notes. The reason why your coils, when you were pulsing, would only pick up in one direction is because you've polarized the media. In other words,
Right.
you've polarized the area. It's called NMR, nuclear magnetic resonance, because you're flipping the poles of everything in the area as it is. I do it all day long. I understand what you're doing. The other one was your potential difference from the inside core to the outside core. When you add
Right.
energy or a load to the inside core and your power supply goes down a little bit, you've got it. The reason why you're only seeing milliamps on your cores is because you're not pulling a load. Your load will now define the power in your system because
Gotcha.
you're there.
Okay.
You've got it. Okay.
Right.
And then
I remember hearing you say that before, actually, that the load is required to draw the energy out. And
yes,
does that change the power supply input? Does that reduce it or increase it?
depends
Or does
how
it
much
stay the same?
saturation, like where your saturation point is for
Right.
the numbers basically go how many windings you have, the size of your coil, and then what you're putting on the inside, and that will define how much you can actually get out entirely. Did I answer the question correctly?
Yeah, it does. It also, I mean, I was surprised it worked at all because I'd lost all the internal angles of the geometry I was trying to make
Yeah.
through the rotation. So
Okay.
I guess, I mean,
You
I
want a
haven't
golden
measured
nugget?
it properly. What's that?
You want a golden nugget?
Sure.
Okay, so Ian, I'm gonna tell them a little golden nugget. My coils, although they're based on sacred geometry, are not based on the shapes of sacred geometry. The shapes are a result of winding the coil itself. So when
Okay.
people are trying to get the shape into the coil, that's not how it works with the way that I've done it. The shape shows up after winding the
Right.
coil.
Gotcha.
Okay, so when you put a pentagram in your new one,
Yeah.
I looked at your number sequence. I don't know where you added the pentagram. I'm guessing, okay, and I could be wrong, and I hope I am. I'm guessing that you're going to get deconstructive interference from that. In other words, it's
Right.
going to do some canceling out. I hope I'm wrong. Maybe you're going to get a multiplication output. It depends where you put it. But I don't play with pentagrams because if you put them in the wrong spot in your system, it literally cancels out. It's hard to explain. It basically cancels out certain frequencies.
Gotcha. Yeah. You know, it wasn't, it didn't really have the right ratio that I was looking for before. I mean, I was happy with the perfect fifths and the octaves, and I think, yeah, because I was using the triangle, square, hexagram, and octagon. I skipped the pentagram for the first one because, yeah, I just thought it just seemed to be applying an overcomplication. But when you start looking at, I'll just show you in a minute. We'll come back to that later because I've got a couple of slides I want to show on that and
Okay.
why I
Yeah.
included it.
I didn't mean to
Because-
interrupt you. Sorry, Ian.
No, that's fine. That's fine. No, it's good. It's good. I mean, if we don't chat about these things as they come up, they get forgotten, and it's great.
Yeah.
I love your input.
And I wanted you to know you're doing amazing work. You're there. You can increase your levels more, but you're there.
Oh, sure. I mean, but none of this would be happening without listening to your nuggets.
Well, there's also Nathan.
I've needed
Yes,
your nuggets to guide me in the right kind of thinking for it, in a sense. So, but it was great. I mean, I did these. I was kind of you were delaying on your presentation, so I thought, well, why don't I translate this into a toroidal form, and see what happens, because that's different. So, but also there's nothing. I mean, those other rodent coils, they're fully wound coils. You know, you're going through the center every time, unless you're using the triangle or the pentagon, so which is the 3 and the 5 points around it. You don't actually need to go through the center at all with the actual spool. You can wrap around the outside and then back through the inside and then to the outside to the equator again, around the node that you want, and then back in. And I've got a little video I can show how to wind it as well. I did this morning when I was putting the last layer on. It's quick. It's not too painful. But yeah, just talking about the form itself. Yeah, it looks a bit scuffed. That was just me getting rid of the support material when it was building on either side and stuff. And I just like it to be a little bit smooth to prevent that, interfering with stuff. The outside, if anybody wants to try and make these, right, I put every other number down. I use even numbers because I can see a gap in between, and I can see the 4 or 6. That's got to be 5, right? And I had them colored before. I didn't really use the colors this time, but that was for the rodent coils, for specifically getting the correct node to wrap around each time I was moving around it. So easy to lose count. So, and also what isn't there is I actually have the number 2, a directional arrow of which side of the former to go with the number 2 coil, and opposite on the other side for the number 1, because I was starting on the outside, coming around, and then I would go the opposite way with the secondary coil because it's counterwound. So that's what that. Those are nylon. Those are 3-inch nylon screws. I cut them down a little bit, but basically they're really handy because you don't realize how much the wire lifts up, and you can unscrew them a bit to get more room, to get more wire underneath as you're winding it as well, which kind of helps. But let's see.
Nice.
I'm going to get my. Hang on, maybe I'll have to do.
I really like your coils, Ian. They're really beautiful. The gold one,
Thanks, Ben.
especially.
Mm-hmm.
Yeah, very much so.
Here we go.
I'm gonna open the
I'll do
box.
this. Yeah, here we go. Okay, right. Here we go. All right.
Yeah. Oh my God.
Oh,
Here's
wow.
It's a big box. I need a big knife.
Here's just a quick video I did this morning. It just shows how the coil is wrapped. So, quick on how to wrap these coils. Pretty much I'm onto the last one.
Oh, wow. That's nice.
Go for the triangles, and then where then pentagrams this time, the hexagon. Basically, you have to your numbers, a lot of numbers. I just use a ruler underneath to keep me on the right place. 2 spools, bifilar coil. So starting off with number 1. So this, I'm wrapping on the outside first, up through the inside.
And trust me, it's the octagon, so it's every 3. So
Yeah, that just looks painful.
oh, you've no idea. My neck was so sore at the end of this from between yesterday and today.
Oh, yeah.
Anyway, I think that's
Basically,
as far
just
as.
do that full way round, but you're never fully encircling it. So when you have an even number of lines, you don't need to put the wire through the center. You can just leave it out here, pull it back and over, basically. And then once you get to the end of that wrap, tube coil, basically go to the same post that you started with this, and then do exactly the same thing in reverse. Here it's 0, 3, 6, 9, 12, 15, 18, 21, back to 0. Then you go 21, 18, 15, 12, 9, 6, 3, back to 0 with this one. When you finish your number 1 coil winding with this, go to the next post and wind it off there. Then that gives you the free post where you ended up with the second coil on the starting point again. That's basically that.
Nice.
Just a quick.
Very nice.
Okay.
Yeah, that's really
yeah,
cool, Ian.
That's
Impressive.
so that's I didn't, I wasn't very clear. I was just I really had to get on with it to get it ready for today. But yeah, so that's the final thing today. And all right, so that's the first 3 winds. So that's where the pentagram is, Gerald. It was slap in the middle, unfortunately. I think that's probably. I thought maybe I'll put it right at the end so that I can unwind it if it causes a problem. But I thought, what the heck? In for a penny, in for a pound, right? So the first one is the triangles, then the squares, then the pentagram, and then that's the hexagram and or hexagon and octagon. So these things
Incredible.
ratios. Sorry?
Incredible.
Yeah. So, but it is, you've just got to put a ruler under the line. This takes you from, say, 9. This is for the octagon, so it goes in steps of 3 because it's a 24 nodes. So you just go in basically 0 is 24 as well, and then 18, yeah, and then back to 0 again. Yeah, so that's right. So you go 9 to 9 and then 9 to 9 in reverse, basically. So it just takes it takes so long to do these things. It's so easy to lose concentration, and then at least you can go back to a number that you recognize if you screw up, and then kick off from there again. But yeah, that's it today. That's just one of the coils. That's the 1.192 millihenries. That's 1192 microhenries. The other one was about 954, something like that. It's just a little bit weird. Yeah, that's yeah. Oh, I'm sorry. That's really blurry. That is, Gerald, that's your basic pulse circuit that you gave that evening. That's what I was using on the experiment. The only difference here is the signal generator positive output. I put a 10K resistor on that just to protect the signal generator from feedback. I don't know.
Okay, so
but that experiment was done with that 10K resistor in place between the base and the generator, pulse going in. It gave more voltage in the system if I took it out, but I just thought there was something that I thought made sense just to protect the generator itself, but that may be bullshit. I'm not sure.
No, that makes sense. I've never used it, but that makes sense.
Yeah. I wasn't sure what was going to happen, so I thought I might as well protect it rather than blowing one of them up, because you got to wait to get a replacement.
You made one difference that I don't. Well, you made a couple actually. I did one of those weird things and ran it backwards again. Okay, so Nathan's laughing at me. Okay, so the positive would go straight to the collector, the negative would go to the coil, and then from the coil, it would go to the E. That's how I
Yeah.
run my pulse circuits.
Yeah, but that's because you're doing it negatively. In this
Yeah.
instance, you said that the coil would probably work better with a positive pulse, and
Yeah,
that's
because of
why.
the type of coil it was. Now I remember the conversation. I apologize. Yeah.
That's right. So that's and I tried the negative, and I don't think I had it connected correctly anyway. I kind of interpolated what it should be, but I'm no electronics guy at all, unfortunately. So I'm totally reliant on other people's abilities in that department. But yeah, so yeah, and then that's the pickup coil there, just going to the 10 microfarads through the rectifier.
Yeah.
Yeah, so I that was a bit of a scribble I did because I remember Nathan had asked me to provide it, but that's it basically.
So here's another
That's
little nugget for you. When I
uh-huh.
pulse my coils and I run the negative part to the battery and then through the coil, because my coil's bifilar, I'm running that circuit in a negative way, right? But my bifilar, the secondary comes out positive. Do you get my point?
Okay. Yeah,
Okay, because if you get a back EMF,
it's
rather
the
than
opposite
run like
polarity.
sorry,
It becomes the opposite polarity.
you got it. So there's another little nugget for you that might help you when you're playing around with all this. If you have a 180-degree out of phase bifilar and you're pulsing your negative, your secondary is going to come out positive.
Right. Okay.
I have to
cool.
say, I like how you have the neon lamps there, covered with the insulation. That's pretty cool. I never would have thought.
Yeah, it was just because the diode was right behind them, and I thought, oh, this will just keep them because I know they get bent, and I just didn't want them to short anything out.
No, it's a good idea. I might steal that idea
Yeah.
if you don't mind.
No, it's just shrink wrap unshrunken, just covering them up
No,
as if just to
yeah.
give them a bit of insulation. Yeah.
Yeah, no, that's
But,
good because I want to encase the little small mini breadboard I have and make it easily swappable for the neon and the transistor. So I think that's a good idea to include that. Thank you.
No, those those are hardwired in between the collector and the emitter, I think, isn't that
Oh
right?
yeah, they're soldered at the other end. That's
They're
fine.
soldered
I can.
underneath.
Yeah, I
Yeah,
can.
but the two sets, the two pairs of posts at the back, those are for the parallel circuits to run off the coils, off the circuit. This is your those are two. Is that the 13009 transistors there? This is your modified Bedini circuit, you call it, I think, Gerald. But it's
Right.
also, but it also has the switch and the potentiometer for the coil geometry that you use, the little one to jump for the magnetic levitation.
Nice.
So
That's a
I
nice
just kind of
touch.
included it in there. But this is the one I just started using tonight, and whether it's the coil is completely different or something, but I need to go through this circuit and see what I've done wrong because I know I've done something wrong somewhere, seemingly. But although I thought I got it all right according to your diagram, Gerald, but I may have done something wrong. But anyway, so unfortunately, yeah, the front two posts are the power supply in, the coil ins and outs for the primary and secondary, the L1, L2, and then capacitor banks can be attached, or the load can be attached to either of those sides, depending on which circuit that you want to put them on. So yeah, so that should work nicely once I figure out, troubleshoot it, and see what's going on.
It's probably
Yeah,
something.
I've been busy making your boards, Gerald, and trying them. This
Nice.
one, this is
Gerald's an
this is the
inspiration.
I'm honored. Seriously.
this is your horizontal deflector circuit. That's the 4099 or something, like the horizontal deflector transistor.
Yeah.
I haven't been able to get this to work yet because I think this is wrong. I haven't wired this up right with everything. And
That's the old version of the modified Bodini. I swapped it out for the new transistors, and that's the 50 ohm 15 watt. I think you were using, and that's yeah, that was
Yeah.
from a while ago. So
Yeah, I recognize
then
those
we've got
capacitors.
oh, and these are still patiently waiting,
About my head.
waiting for Joe.
Nice.
All right, that's just I'll try not to wither on too long here, but this is I'm not sure where this was from. It might have been from Alchemical Science. I think it was actually. He did a nice presentation on this subject. It's all part of Malcolm Bendel's kind of theory, but it's just basically sacred geometry. But what that video you put up a few weeks ago about sonic geometry, I don't know why, I'd never made the connection between the internal angles of geometrical shapes and the output tone that they made in hertz. And I thought, what an idiot. I never thought of that. And that's why I put the pentagram in this one, because it's a 540, and that is actually the that denotes the third of the major triad. I think that video it began with F sharp as basically as 180 as the root.
Yeah.
It depends really on the math you use to get to different note equivalents.
Yep.
But I'm not sure that really matters too much, so long as the correct note frequency sequence is in place. It creates any major chord, no matter what you do, where you do it. So yeah, so this one, he talks a little bit about it. I just wanted to bring that up. Basically, this gave me that. It also, the nice thing is, when you look at the numbers here, everything again, it's all mod 9. Everything is divisible by 9, and additively multiplication, it all goes to 9, and you'll see all the numbers here are add up to 9 as well. So it's 1, 2, 9, 6 is 1 and 2 is 3, and 6 is 9, and 9 is 18, which is 1 and 8 is 9. So this happens throughout the whole chart here. It doesn't leave any room for my Pythagorean comma thoughts, but it is nice because everything is a whole number, and electrons' valences are only whole integers. They're not fractions of. So these are the obviously 3D geometry shapes, platonic solids, and again
Now
we've
you're
got the
talking.
same numbers coming through in here. So it doesn't matter whether they're flat or three-dimensional, they all come up with the same ratio, the same relationship of numbers, and also the same chords. So so that makes me think that if the curvature of the wire going across the toroid form is somehow preserving something, or as you say, Gerald, creating the shapes through, and it could simply be the wire length, because I think the wire lengths should still be at the correct ratio for each
That's
side
part of it.
that is turned, because they're all doing the same rotation around, but they're shorter. The nodes are shorter together for, say, the octagon compared to the triangle. So you got much longer length of wire for the triangle. So the length of the wides are still proportionately the same.
Yeah.
And then everything, if you look at Buckminster Fuller's buckyball, when he has it collapsing and expanding, I mean, it's going through all different geometries to get to one end or the other. So
Absolutely.
there is movement everywhere all the time, and it's not set. So,
But that's the
again,
movement that makes the sound.
right, okay.
Okay,
And
so
again, here, this is the diagonal going up there. So those are perfect fifths. Again, it's using a doubling on the first column. Every column is a doubling. You see like 81, 162, 324, 1, 2, 4, 8, 16, 32. And then it's tripling along the top. So you've got that 3 to 2 ratio, but it shows you where the perfect fifths are aligned.
256 is normally denoted as C. And then you're working up in fifths. So that would be C, that would be G, then up to D, and so forth. And then that you can basically derive the whole diatonic scale, the Pythagorean scale, through the fifths movement up the scale. So I thought that was interesting. Chromatic scale, I'm not so much interested with. But the interesting one here was that if you can change the amplitude by shifting the starting point. If you go, you see in the center one at the back, it's got a different set of numbers and a different set of sequences going on, but they are basically the same numbers, just with a decimal point in there. But it's another take on it. And the only place I can get F sharp to be 180, I think was in, I'm sorry, I put these up. Oh yeah, there it is, F sharp, at where 90 and 20 intersect on it. Right here is 180.
Okay.
So that's by multiplying it by 10, by raising everything by a factor of 10, then you get F sharp to be 180. So I'm not sure. So you've got 1, F sharp is going to be, well, it's a completely different number, and 0.1, again, your F sharps are, that's those are Fs actually, because he hasn't put F sharps in here, but anyway. So yeah, just thought that was interesting, because that's basically why I put the pentagram in, because that is part of the major triad, and I thought I probably shouldn't leave it out. And this is how he does it, with doubling and halving in one direction, up, you're halving, doubling on the bottom, and still multiplying by 3 along the rows. So
You want to hear
anyway.
something funny? I haven't put a pentagram in any of my coils. Not one.
Not one?
Not one.
Interesting. Or did you not try one and then find it fail and not use it again?
You could say something like that. I was playing with Starship coils and different frequencies, and then I built one of, it was not just the pentagram that was in there, it was the pentagram and the triangle, and I ran certain frequency through it, and I didn't like what happened after, so I ripped it apart and never put them in any of my coils ever. I don't know if it was because I didn't know what I was doing at the time, or if it was because of that very geometry, but I never took the risk.
Okay. Did you, whereabouts in the coil was it? In this case, it's in the center of this one. It's the third of the 5.
Yeah, it was towards the bottom in this one, because it was triangle, then it was the pentagram. So
right.
Yeah, but
okay. Well,
I don't know.
I'll bear that in mind for sure. Then I'll just keep an eye on it. I was wondering what was giving me a sore neck and shoulders when I was making it. Maybe it's after I put the pentagram in. You never know.
Certain geometries I don't play with, right? And that's one of them. Just saying.
All right. Okay. Cool. Well, that's good to know. Thanks.
Yeah, it's more of a destructive interference, that pattern. Really? Not constructive. It doesn't build upon. It more takes away.
Right. Huh. Okay. Well, I'm going to set up exactly the same experiment as I did before, with the same solenoids, and I'll see if there's any difference.
Yep.
I mean, obviously, I've made a couple of changes. It's by filer now, but yeah. All right. Cool. Oh, just to finish, I saw a presentation. That is Adrian Marsh. He's a British physicist, basically, but he's an expert in making the golden dragon discharge from his coils, and he uses all kinds of modulation and amplifiers that he makes himself, or he adjusts. I think Hewlett Packard ones or something, or no, Kenwood amplifiers. Anyway, he and Eric Dollard work together on this kind of stuff, and for the builds that they do to get these, but look at all those tendrils and everything on the way up. It's basically it's called the Golden Dragon because it follows the golden ratio in its curvature, and Yeah, he does it in parallel mode as opposed to series mode for his resonance, because he says it with his system that works better. But I just saw that, and I took a screenshot of it from his presentation. Naughty me.
Amazing.
I thought it was so beautiful that it was worth sharing, just because yeah,
You almost-
AMI,
It's art.
Yeah,
Yeah,
it is art.
absolutely.
Beautiful. Yeah.
looks like a dragon with its tail coming out and its arms going, "What are you doing?" That's awesome.
Got a couple of big talons there as well.
Yeah.
Yeah.
Nice.
Those are not easy to make, it seems. So I just thought that was worth sharing.
Mm.
Oh,
Very
right.
cool. Nice work,
Yeah.
Ian.
Yeah, thank you, Ian.
Yeah, thanks, Ian.
You're welcome.
Awesome.
Oh, what the heck was that?
The whistle pop. It's a celebration.
Wow.
You're gonna
Oh,
hurt
that's what-
Ian's
Damn
ears
candies.
or Nathan's ears because
It's
Yeah.
killing me over here.
yeah.
Oh, was there some erroneous noise?
Oh, my bad.
Thanks, Ian.
Did you like
Great
my
job.
box opener?
Ooh.
That's a little excessive.
Yeah, I'd say.
I think
It
you
was a
killed
big
the
box.
box.
Nice.
Required a
Yeah,
big
we'll-
knife. That's
Nice.
the knife out of Rambo 3, eh?
Wow. It's a sword.
It's big.
Yeah,
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 it's
really.
well, I don't know. It's kind of
it's a sword.
yeah.
It's a
It's, small.
sword.
It's like the Roman, you know.
Gladius.
Yeah.
Yeah.
What do
Yeah.
they put a slit in it for? Is there a purpose for that?
Make it lighter.
Well, make it lighter, and technically, when it goes in, it'll create suction if there's no hole there. But with that hole there, and it comes out. For deer. I'm just saying.
Sure. Yeah.
That's
Got
what
big
the hole's
deer.
for.
Yeah, I think we're way off subject there on that.
Yeah, I apologize.
Well, thank you, Nathan, for having me on.
Yeah, thank you,
Great.
Shawn, for coming on and presenting and hanging out with us and doing everything else.
Amazing work, Shawn. Absolutely.
Thank you. I
And I-
appreciate it, guys.
I gotta have
Yeah.
a conversation about the Death Star. Off air
Sounds-
first.
Sounds good. Sounds good.
Have you've made one, Gerald?
No, but you guys have, and I think I found a purpose for it that's not what you guys expected, but we'll get into that off air
That's
because
good.
it has to be tested. Otherwise, it's just hot air coming out of my mouth, kind of thing, right?
Yeah, I'd
Okay.
love to hear your thoughts. Thank you.
Absolutely.
Also, and Gerald, it'd be great to see that horizontal deflection circuit. You've done most of it.
yes.
It was just been the coil attachments, the coil connections.
Did you want me to do a video like I did the last time with the drawn out circuit? Did that help at all, or?
Yeah, I mean, anatomically, it was beautiful. Yeah,
I'll make sure it's nice and bright then.
Any way that works for you, Gerald, is good. I mean, it could just be a schematic or a drawing, just so long as it's just getting the connections right. That's all that really.
The
really
horizontal deflection transistor is the same as the regular pulse circuit.
Yeah, I haven't
like-
been able to get that to work. The regular negative circuit pulse.
Yeah, but you're using it on the positive end.
No, that works. It's when I try to do the opposite, it's not working for some reason, and I'm not sure what I'm doing wrong.
Maybe it's the well. That's interesting. It shouldn't be the.
Well, no, I
coil,
mean,
because
I'm measuring the actual pulses I'm getting from it on the oscilloscope, and it's not right, basically. So I've obviously done something wrong somewhere. So yeah, but if you wouldn't mind, that'd be great. Just sometime, that'd be useful.
Yeah, not a problem actually. I'll do a video on it tomorrow. I'll pull it out and then I'll draw it out, and it won't be anatomically correct though. No, I'll get it done for you tomorrow. No problem.
All right. Cool.
I mean, I could show you now,
Nice.
but go ahead.
No, whatever works, Gerald. I mean, I've got a couple of days left. I got to pack up and go back to work anyway, so I'll probably be making it at work next week.
Hold on, don't tell him that. Don't tell him that because he won't,
No, I
won't have
know,
it for
I
you.
know.
No. Just write it down for him, please, Gerald, immediately, and just put it on your channel.
I
We
already
would
did.
really appreciate it.
Yeah, it'll be done by tomorrow.
Cool.
Got it.
Yeah, just for the guys in the chat, thanks very much, but I can't comment because it's asking me to connect my account for some reason. I must have signed out or something like that. But I'm not able to respond to them. There's always
Gotcha.
something. Anyway, but thanks.
Yeah, they're pretty
Okay.
awesome in the chat, man.
There, it's on the whiteboard.
All right.
All right. Thanks, Gerald.
Good deal. All right, guys. It's been 2.5 hours. We're about done here.
Wow, blink.
Oh,
Time
wow.
goes by when you're having fun.
Oh, man.
Oh,
Two awesome
I'm sorry.
presenters today.
Yeah.
Yeah, so
Yeah, sorry.
Friday, we're doing League of Extraordinary Gentlemen. Ben and I are going to be hosting it for the next 2 weeks. So everybody's welcome to come on. And then we'll get a hold of Phil. Then we'll also get a hold of Lulu. And we'll just have a nice, fun time.
I'll be there.
Nice.
I'll have my hat on straight. We'll get her done.
Cool. All right, well, thanks for listening.
Yeah, thank you very much,
Oh,
Ian,
thank
for
you for
doing this. I
being here,
appreciate it.
Yeah,
Absolutely
thanks, Ian.
amazing.
And Sean too.
Yes.
He's,
very
Yeah,
much
John,
so.
excellent. All right. Thank you.
All right, guys. Have a great
See you
night.
then.
Thank you for chat.
Everybody,
We'll see you guys on Friday. Have a great night.
Thanks, everybody. Thanks, Gerald, Ian, Nathan, Chad.
Ben, Ian, Nathan, John.
Good, Don.